I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for your students. Pray that you just guide our work today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. I don't know, I don't know if I've ever talked about it or not, but every once in a while you'll see people reference the what Artin did for Galois theory, like his textbook on Galois theory. So here it is, Emil Artin's Galois theory book. This is a Dover, and I was looking at it because I was like, maybe I can find some different examples in Artin. So then I was looking. That's not an example. Theorem, proof, theorem, proof, theorem, proof, theorem, proof. I don't think there's an example in this. I mean, I couldn't find an example. I mean, maybe there's one hidden in here somewhere. I mean, there's some sort of like Uber examples, right? But it's like, yeah, it's exactly, it's 80 pages, right? So it's kind of shocking. Well, there's kind of an example at the end, I think, a little bit, but I don't know. That's Artin's 80 pages. All right, so I gave you guys the take-home test. That's due not this Friday, but next Friday. I hope that's enough time for you guys to get it together. I should probably assign other homeworks, but I probably won't, unless something just pops out at me as being important, because I think this is probably enough to keep you busy. And after you understand this, you should be pretty well prepared for the test, I would hope. I'll think on that more as we go on here, but all right, so any questions about anything? All right, good, you call my bluff. All right, so let's see here. I didn't call my bluff. Let's see here. So this brings us to section 14.6. And again, I'm sorry I never actually posted that video I was threatening. Eventually, I'm going to make good on those threats and get back our class days, but it just hasn't happened yet. So this is Galois groups of polynomials. Galois groups of polynomials. And what's done in this section, as I told you guys before, is just fascinating. Really is just fascinating. And so he starts out the section, Dummett and Foote, of course, by basically showing that you can literally think about the Galois group of a given polynomial as just permutations on the roots, right? And so he has an explicit example where he does that. And so that's basically the idea, is to look at the Galois group as permutations on the roots, rather. So here's a definition that we'll get to work on here. Let x1, x2, xn be indeterminates. All right, be indeterminates, then the elementary symmetric functions all right, S1, S2, all the way out through Sn are defined as follows. All right. So how's it go? So first of all, S1 is just equal to x1 plus x2 plus plus xn. All right. So it's symmetric in the sense that no matter what permutation you made of the symbols 1 through n, you'd still have S1 as fixed. That's what it is, right? It's completely symmetric in terms of permutations of the indices 1 through n. What's S2? x1, x2, plus we got x1, x3, x1, xn, and then what? All right. So it doesn't start from 2, 1. It just does. It starts from 2, 3. So then like 2, 4. x2, xn. So I guess here, just to count, in terms of the summands here, there's n of these, right? Or no? Does it start with x1, x1? No, it does not. Yeah, n minus 1. This is n minus 1 of these terms here. And this would have n minus 2, right? Because it starts from 3. And then you keep going, right? What's the next one? x3, x4? And so forth and so on. Eventually you get to what? Xn minus 1, xn, yeah. All right. And he says, so forth and so on. Eventually, the nth one would be, let's see here, x1, x2, xn, right? So these so-called elementary symmetric functions. He says the ith symmetric function, s sub I, is the sum of all products of the x sub j's taken I at a time, without repeats. He didn't say that. I added that. But I guess it's obvious from his examples, right? Have you guys ever seen this in any other class? Oh, Daniel, you don't count. No. Yeah, they came up in advanced calculus in a weird way, right? There was some, I even forget, what was that homework problem even? I mean, it was something, it was technical, and it was some weird linear algebra stuff is what it was, right? That's the only place I remember seeing them before, and yet these are like bedrocks of like mathematics. Like this idea of symmetric functions has been around for a long time. Like this is not some kind of new idea. Lagrange played with these things. Like all of the great mathematicians of the past millennia have worked with these things. Question?
Can you say what S3 would look like?
Fair question. I can start us. S3 would be x1, x2, x3. x1, x2, xn. Plus plus xn minus 2, xn minus 1, xn. I mean, pick your favorite
Wait, so your next one, you wouldn't go x1, x3, x4?
x1, x3. Yeah. So you're going to have to cycle through the complete lexicographic ordering of the symbols 1 through n. There's a lot of things there, indeed. Yeah, it's quite awful. Okay, so these are elementary, quote-unquote elementary symmetric functions. Yes, what's that? So definition. So this is sort of the blank template on which you can draw Galois theory, the general polynomial of degree n. What's this look like? General polynomial of degree n is the polynomial x minus x1, x minus x2, x minus xn, where whose roots or roots are the indeterminates. So sorry, it amuses me more than it ought to. Indeterminates x1, x2, xn, right? I think he's defining roots for a polynomial built from indeterminates here, by the way. That's also defining the term roots, I believe. I mean, if it's an indeterminate, I don't think I should think of it as, I mean, you can think of it, but in the abstract, it shouldn't be an element of a number field, right? And yet our roots are elements of number fields, right? I think. So there you go, general polynomial. So this is, so the idea of using indeterminates here is what? This captures just what an arbitrary nth order polynomial looks like, right? Without making a commitment to specific choices of roots. So all of the particular structure that makes a given nth order polynomial what it is is kind of just removed by working with indeterminates. So I mean, that's kind of the idea. Well, it is the idea. It's not kind of the idea. I use kind of too much. Now he says that it's easy to see by induction that the coefficients of the general polynomial or degree n are given by the elementary symmetric functions of its roots. And I think it would be a good exercise for us to do this at, say, n equals to 2 and see how that fleshes out, at least to start with. Maybe work on n equals 3. So, great. Let's see here. Stink. All right, example. X minus x1, x minus x2. So we got x squared minus x1, x minus x2, x plus x1, x2. Yes. In other words, x squared minus x1 plus x2 times x plus x1, x2. It's okay. I recently got some videoing. I said too much about Disney World the other day, and I had to edit it out. And well, I'm not going to repeat it here. I've had enough editing for.
You're already editing this video.
What? Why? Oh no, not copyright. Just other things. I'll tell you after class. Let's see here. So S.
No, it wasn't that he's talking about. It's what he said about Disney.
It's how I said what I said about Disney World.
Okay.
So this is S. So now the symmetric functions depend on I mean, there's a different set of elementary symmetric functions for each choice of n, right? And for arbitrary n, it's quite onerous. But for n equals 2, well, this is S1. And this is S2. And there you have it. X squared minus S1 times x plus minus 1 to the 2, S2. Well, this was fun. Let's do another.
Is this like where the functions are like initially defined, or like where they're going to come from, or is this like...
Oh, where do elementary symmetric functions come from? That would be a, you know, honestly, Jess, I think that might well be a PhD in math history. I mean, I think that's a difficult question. Not just here. I mean, certainly, that's a good question. I mean, this is probably one of the more interesting places they were first played with. I don't know. I don't have a good sense of the answer to that question. But I know that this idea that you can take an equation where different variables are appearing symmetrically, and if you can make some kind of variable interchange, they come up in that idea. Anyway, so we can multiply this out, and we get x squared minus x1 plus x2 times x plus x1, x2 from the product of the first two, right? Because we just did that. Yes. So having done that, we can now piggyback off the last example, and this gives us x cubed. And you see what's going to happen for the linear term. On the one hand, I mean, for the quadratic term rather, on the one hand you get the product of this and that. I mean, you could go with this, or you could go with that. So you got that. And so that gives us our minus x1 plus x2 plus x3, x squared. And then how about the linear term? So the linear term is coming from what? It's coming from x1 plus x2, x times that x3, right? So that's giving me like x1, x3 plus x2, x3. I'll use some color coding to indicate where that came from. So this piece right here is coming from the product of this guy and that guy. And let's see here, what else do we have in terms of x terms? Oh, we also have the, yeah, this piece right here, right? So was it plus x1, x2 times x? And then finally the easy one, minus x1, x2, x3. Right? So, yeah, lo and behold, what we got here, in terms of n equals to 3, this is S1. This is the second elementary function, and here's the third elementary symmetric function on 3 symbols. Now his claim is by induction you can show that this pattern continues for the arbitrary nth order one. So basically by induction, which you can start to see how the induction works here even, right? So theorem is just x minus x1, x minus x2, dot, 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 x minus xn is in fact equal to x to the n minus, it's minus, right? It's always minus. It always leads with a minus, doesn't it? Yeah. Minus s1 times x plus s2 times x squared, and then so forth until we get to the last one, which is minus 1 to the n Sn, right? So that's the relation between the elementary symmetric functions and the arbitrary nth order polynomial. Here the Sn is Sn. I mean, this one is S3.
Yeah.
That one's S2.
Yeah. The degree of x. Yeah, minus 1. S1 x to the n minus 1.
Oh, that's, you're saying it's Sn minus 1?
X.
X to the n minus 1.
Oh.
You go x.
Oh, whoa, 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 whoa. I'm an idiot. Yes, absolutely. I do not disagree with that whatsoever. You guys are right. Yes, thank you. Thank you. No, no, no. I was, see, John, I thought you were talking about this piece. You're talking about that piece. That's why I was confused. Okay, gotcha. Oh, no, what have I done? Where there's smoke, there's fire. Let's see here. Let's see here. Okay. Any other mistakes I made on purpose for your learning here? I don't know. Yeah. You're welcome. I'm sure I can find more. Daniel, is that mic plugged in? Because I had a problem here earlier with it. It's bouncing. Okay, good. Somehow it didn't plug the mic in this morning, and I usually don't care that much, but I have some students out with the flu, and so it matters more at the moment. Not you guys. 1, 2, 3, 4. Wait a minute. Who's missing?
Audrey.
Who?
Audrey.
Oh, Audrey. Yes, yes, yes. I know Audrey. Like, who's Audrey? Who's Audrey? Sadness. I know who Audrey is. I'm sorry. Let's see here.
Might want to
Edit
edit that out too.
that out too. Audrey can't fire me. Let's see here. I might have to edit that out. Let's see here. Man, this is going to be a heavily edited video.
What was class for 15 minutes today?
There's like 15 minutes left of it? Yeah. All right, so here's what he says. He says, for any field f, the extension f adjoin the n indeterminates is a Galois extension of the field. Let me just write that down. It's a lot to say. So he says observation. So here's the observation. F extended by x1, x2, xn is a Galois extension over the base field f of the elementary symmetric functions S1, S2, Sn. Why is that? Is it you said this is a subfield?
Yeah.
Okay, well, I mean, yeah, I guess point number one, that better be the case, right? If that's not the case, we're definitely out of luck. So, I mean, that's the first thing that we need for an extension, is that it's actually a subset in a natural way, right? But the fact that that's a field and that that's a subfield means it's an extension field, but why does it mean it's a Galois extension? That is important. I mean, that's an important point, but we need to. What was the most useful characterization of a Galois extension here for us is that of a splitting field. All right, so let's think about that too. So if we have, say, f of x in this guy. It's such a pain to write all this. So this thing, polynomials with coefficients in the symmetric functions. So if the coefficients are now I just need to see a specific example. I mean, so let's just try something simple and see if we can understand it a little bit more concretely here for just a second. Was there something, Daniel?
I'm just trying to, what did you mean by f of x1, x2, over xn being a field?
Oh, well, that's just like another example of that would be, what's this? R of x, right? This is the, yeah, it's the, but yeah, I believe it would be rational, essentially be rational functions in those. Yeah, it's big. Yeah. Okay, I digress. So how about this? What would be a typical example in here, just to get a better sense of what we're doing? What if I had like f of x equal to, I don't know, x squared plus s1x plus s1, s2. I mean, that would be something in there, right? Why are we able to? Because he claims that the f adjoin the indeterminates, that field, is a splitting field for the field built from the elementary symmetric functions. That's what he says. I mean, he says the extension by the x's is a Galois extension of the extension by the s's, since it's a splitting field of the general polynomial of degree n. Oh, it's not just any polynomial, excuse me. Not just any polynomial. It's if we have, I need to make it the n Pacman, so I'll put an n here. So like this polynomial, this particular polynomial. So this polynomial, right, which is certainly in here, right, is split in there. This polynomial is this is a particular polynomial with coefficients of symmetric functions. It is split in the extension by the indeterminates. Does that make sense? No? This formula. This is the polynomial, and here's its factoring.
Okay,
f of
Is that also like
I mean, a typical, I mean, I don't know if this is, maybe we shouldn't say rational function. I think I probably should say, maybe I shouldn't say that. Maybe I should say, like our usual thing, this is what, I'm sorry, I shouldn't say rational functions, Daniel. That's the source of your trouble. This is, I mean, I think we basically look at this as an n vector with basis x1 through xn and coefficients coming from f. So like a typical thing in here is like c1 x1 plus c2 x2 plus c3 x3 da 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 da.
right, but how is it a field?
Oh. With multiplicative inverses. Yeah. So maybe we're back to what I said before, but it seems to me the question of can you construct that is a separate question than the one we're mainly interested in here at the moment. But
Well, that aside, it makes sense.
that aside, that makes sense. So, fair enough. So yes, this is a Galois extension because it splits the general polynomial of nth order, which I have taken to be the nth Pac-Man. All right, so okay. So if sigma is, let's see here. Let me write this out here.
What if like extends weren't necessarily in that order?
Well, I mean, it's this specific polynomial that it's the splitting field of. Like this here was not, I mean, even though well, I got the wrong sign here, right? So even that wouldn't work, right? I mean, I need x squared minus s1x plus s1 s2 for f of x1 x2 to be the splitting field of f of s1 comma s2. Now, of course, f of s1 comma s2 has s12 in it because it's got products. Yeah. Oakley dokley. So here's the next little blurb here. He says, if sigma, an element of Sn, right, is any permutation of 1 to n, then what do we say? He says, then sigma acts on the rational functions there you go, Daniel. Rational functions in right? How does it do it? How would you act on rational functions built with end indeterminates? John says like this.
No, that wasn't, that was me thinking.
Oh, that was you thinking. I thought you were actually showing me what to do with the roots. But my suggestion would be that sigma takes, a particular rational function of x1, xn, and it just maps it to f of x of sigma 1. X of sigma n would be my guess. I mean, like, for example, if sigma is just the 2-cycle 1, 2, and you have f equal to, x1 plus x3 over x1, x2, although that would be bad. In fact, that would be forbidden because, oh, wait a minute. Oh, I could do that. Right, this is a rational function in x's. And how would sigma acting on f, what would that look like? I'm not endorsing this notation as the official notation. This is a temporary thing for this particular discussion. So what would that, I mean, my thought is what? x2 plus x3, yeah. So as you can see, this is not equal to f, right? So under the action of this particular permutation, f is not fixed, for example. But he says that, yeah, you can act on rational functions by permuting the subscripts of the variables. And he says it's clear that this gives an automorphism of the field adjoining the indeterminates. So he says that this will defines automorphism of fx1 xn. I really need to come up with a name for that stupid thing, but oh well. Like I said, f adjoining the x's. All right, he says if we identify sigma, the permutation, with this automorphism, then under that identification, we have Sn as a subgroup of the automorphisms on this thing. So this suggests that we can view Sn as a subgroup, basically that this is in the automorphisms of this guy. By this rule, right? We take any Actually, that one kind of petered out at the end. I'm gonna hurt my throat, you guys. Stop tempting me. Wonder who it is.
More editing.
To complete this someday. He does that, I should walk over, open the door. Or I should just hire some student to go over and like laugh in his class, just open the door and laugh really loud and walk away. Times like this, I really wish we had fraternities. But on the other hand, I don't miss the naked people running around during Pledge Week. So, although one of my favorite memories from NC State, though, it was once I was walking across the brickyard, minding my own business, and all of a sudden some dude comes trucking through there in his tighty whities, and he's booking it. Man, and brickyard is bricks, just like it sounds, right? And he's just running full speed in his tighty whities, and then he catches his foot on something, and he just goes, vroom. But then like a seal, he just pops back up and keeps running. It was amazing. So under this correspondence, the permutations, Sn, we can view them as a particular subgroup of the automorphisms of this thing. All right, so we have that. What? Too much of a hard transition? See, you guys, we don't have that here. You know? Think of what you're missing out. I mean, yeah, we're catching up. I mean, we got girls in pajama pants. We got the pajama pants people here now. We got that. The barefoot. Not if you're a professor, though. So you're.
There's like a couple of them.
They got in trouble for it in the past. Are they? They're. Oh, they're allowed now.
Well, himself thanked Dr. Howell for some help on a project by saying he could go barefoot anywhere he wanted.
The elementary symmetric functions.
That's a true yeah.
The elementary symmetric function. I got enough editing to do already here. The elementary symmetric functions S1, S2, Sn are what? Are fixed under any permutation of their subscripts, right? Right? So in other words, this list would be equal to the same list if I did. I mean, it's better than that, right? In other words, S of, stink. I guess that's kind of complicated to write, but I mean, S sub j is what? It's the product of xi1, xi2, xij, right?
They also it's some
Oh. Oh, I think I got the wrong thing then. It's just a sum. I got the product here, right? And so the point is that this is equal to, I mean, this is the sum over what? Distinct j tuples of n sub n. So same if we do, see, because that's just all it's doing is just sorting through the same bunch of products in a different order, right? And so the point is that these are equal. If you just permute the indices of the subscripts, we still have the same symmetric function, elementary symmetric function. He says, yeah, this is why they're called symmetric. Okay, fine. Which shows the subfield is contained. So he says this guy is contained in the fixed field of what? Of Sn viewed as a subgroup of the automorphisms of the f extend by the x's. Right? Again, viewing the copy of Sn under the correspondence that we talked about over here. So it's in the fixed field of this subgroup of the automorphisms, right? Because in particular, it is fixed by, because this thing I just did here, this is exactly how permutations inside the automorphisms work, right? They work by permuting the subscripts. That's the rule we wrote over there. So then what? Aha! By the fundamental theorem of Galois theory, what have you guys done to me? Galois theory. I said Galois. Good grief. For shame. Oh, it was not a joke. That was just a, well, yeah, it was a joke. It was a joke. It was a joke. It's definitely a joke. All right, I will eventually get through something here. Where was I? By the fundamental theorem of Galois theory, otherwise known as what do we have? The fixed field of Sn now you guys tell me why this is, has index precisely n factorial.
part of the fundamental theorem of Galois theory, right? The index is going to be the same thing as the cardinality of.
Right, so that's the thought here. In case you guys forgot, the cardinality of Sn, the number of things, the number of permutations on n symbols, there's n factorial, those guys. Now what does it mean, though, to say that the fixed field has index n? What does that actually mean? So he says this. We also know this, right? Since it's a splitting field, we have that f of x1, this is a separate comment. So this extended over f s1, that is less than or equal to n factorial. Why is that? Oh, that's because, I mean, this goes back to an earlier thing in chapter 13 for Dummett and Foote, where we proved that the splitting field of an nth order polynomial is at most n factorial in dimension over the base field. So this is splitting field of the n Pac-Man, or the nth order the general n-thoritic polynomial, right? So that means that it has at most degree n factorial over the base field of S adjoining the elementary symmetric functions. Now, what about this index business? So what does that mean, fixed field? Fixed field of Sn has index. How should I picture that? Index with respect to what? I mean, I can draw a different one. I think I can explain index over there. If I look at Q join root 2, root 3, right, or as he calls it, the biquadratic field, we've got these guys. Right? Was there something else?
Root 6.
Oh, right. Was that in the middle? And then these guys, Q, right? And so these were all degree 2 extensions, weren't they? So I'm thinking that the index has to do with this index, right? So what precisely does that mean, the fixed field of Sn? Where is that in like my my field diagram? What should that look like here? I'll start us out. I'll put the thing down here. S1 Sn, right? And then up here we've got our extendo field, x1 xn, right? In principle, we have this intermediate field of the fixed, right? Like somewhere in here, we've got the fixed field. I should call this thing. What do you guys want to call the fixed field in the middle? Okay. All right. So okay, and like that. So the fixed. What is Sn? I'm trying to see where. This sentence is vexing to me. Where is this in everything? Because what he says, right, next is, it follows we actually have equality, and that f s1 Sn is precisely the fixed field of Sn. So I guess it's that if that's the fixed field, this has to be n factorial, if I understand this correctly. This has to be n factorial. Well, I guess I don't know that. I mean, we can think about K being the fixed field of Sn, right? And if it is, it has index n factorial over what's below it, I want to say. But on the other hand, all of this, it has index n factorial, like that. So that forces K to be, well, yeah, so I was about to figure that out. Thank you. By process of diagrammatic inevitability. But yeah, so that forces K to be equal to that, basically. So let me just write that down, just to. I still haven't quite come to terms with the way they talk about fixed fields. They know something I don't know. And I feel like they're abusing the term index, which is probably, I mean, that abuse is, whatever. I'm most likely wrong about my comments there. Let's see here. Where was I? So, consequence, therefore, f of S1, S2, Sn is the fixed field. Remember that correspondence between subgroups of automorphisms and the fields which they fix? Well, we're talking about that again. So this is the fixed field of the copy of Sn, which is hiding inside the automorphisms of the f adjoin the indeterminates field. So let me just state for you the chief results that we get from this. That'll probably be it for today. I don't know about you guys, but today has been productive for me. I understood something today. That doesn't always happen for me. If I find a marker that works. Proposition 30. The fixed field of the symmetric group on n symbols acting on the field of n indeterminates, right, is the field of elementary symmetric functions, in particular f of S1 and S2. So here I'm really just reiterating what we just figured out, right? Proposition 30 has just been proved in our last 20 minutes of conversation here. And we also have a definition. Any rational function f of x1, x2, xn is called symmetric. What does that mean? If what? If it's not changed by a permutation of what? x1, x2, xn. So you can switch the variables around in their ordering, and it doesn't change the rational function. And then finally, corollary 31. This is the fundamental theorem on symmetric functions, or the FTSF. Sorry, let me write down those useless letters. It gives me joy. Any symmetric function in variables x1, x2, xn, what? Is a rational function in the elementary symmetric functions. The proof, I think the proof is one line. What's his proof? He says a symmetric function lies in the fixed field of Sn above. Hence, is a rational function in S1 through Sn. Right. Again, a symmetric function lies in the fixed field of Sn. Right? Hence is a rational function. Does that make sense to you guys?
Yes, but question, I think it's fixed by permutation of x1, so it's fixed by Sn.
So it's just another way of saying we can permute the indices. I mean, it's just a different packaging of permuting the indices, really. So, and then he's got a bunch of examples which are pretty nice. And that brings us to theorem 32, which I'll start with next time, which is that the general polynomial over the field of elementary symmetric functions is separable with Galois group Sn, which is really the takeaway thing from this, which is gives us that for a generic, just a generic nth order polynomial, the Galois group is Sn. So we're almost to that. And then the rest of it, the rest of the section, he's got fancy stuff about the discriminant and particular formulaics for cubics and so forth. I'll try to cover that stuff next time. But anyway, this take-home's due next Friday, and I should more or less be able to follow the... So we'll have the actual in-class test will be the Monday after that. So that would be March 1st maybe. But oh man, March 1st before test? That seems like, wow, this is such a luxurious pace. No? No, sorry. I will eventually try to get your homework back to you with some comments or something. Yep.
What did you say bad about Disney?
Are we